will drag in, but I know Oklahoma State today decided to do their fall break today instead of fall break last week, which was weird because our calendars were supposed to be mesh. And then, from what I understand, really weird at OSU, the offices aren't closed at OSU today. Everything else is open, they're just not having classes. It was weird. So, we will get started. So, we talked about momentum, and there are two types of collisions. We have an elastic, and I know it's not up there yet, so hang on. I gotta hit the right buttons. I haven't hit the right buttons. Let's see if that works. Alright, yep, it looks like you've got it on the screen over there. Technology has not been kind this week. There have been several different episodes this week where technology has failed us. So we have elastic and inelastic collisions. The thing about an elastic collision is it's a special case. And in that special case, kinetic energy is also conserved. So we get two types of collisions. Inelastic collisions are going to be ones where kinetic energy is not conserved. And usually what you can tell with an inelastic collision is I'm going to have some part of the energy is going to end up in sound, light, and a lot of times when we're working general physics problems, we've actually combined the masses, okay? We've actually combined the masses into something else. But elastic collisions are going to be like ball bearings, cue balls, pool problems. So if you've ever seen the trick shots in billiards and pool, that's all about dealing with momentum and how the momentum is coming into play in order to get those trick shots. So what we're going to do right now is we're going to look at it. We looked at collisions in one dimension on Wednesday, and now we're going to look at collisions in two dimensions now, just so that you guys have a chance to work the problems, because the homework for this chapter is due on November the 1st, which is a week from today. And we are into November, so that means we have next week, 3 weeks in November, a week in December, and then it's finals. We're getting close to the end. So let's look at this. So if I've got a mass that's traveling in this direction, and we're going to go ahead and say that this is a 5 kilogram mass. We're going to say that it's traveling at 2 meters per second. And we're going to have it come to the intersection of whatever it is, if we're playing air hockey, or we're playing bumper cars, or we're playing something. We've got another cart that's coming in from the bottom direction. And it's going to have a mass of 10 kilograms, and it's going to be traveling at 4 meters per second. They're going to hit this spot here. We're going to get a crash. And we're going to say that these two things combine together, and they're going to move off in some other direction. And we want to know the magnitude and direction of the final velocity. Right? There's a couple ways we can approach it, because we do have direction. There's a couple of ways that we can approach this problem. One is we can approach it straightforward with vectors and do vector addition and all that good stuff. Or there's another way that we can look at it in terms of its components. And my recommendation that it really does help out if we look at the components, because you can keep track of the x direction and the y direction pretty easily. So what you can do, if we keep our picture there, what we can do is we can set up a table that says here's my x, here's my y, and this is my initial or before, right? This is my before, and this is my after. So this is my final, and I still can't spell after, this lovely week. So I've got my before and my after, and I've got it in terms of its individual components. So in the x direction, the momentum before is going to be the mass of car 1, velocity of car 1. And the after because they're going to be combined, and I'm looking at my velocity vector here, this is going to be some angle at that point. So I'm going to have the combined masses of the two cars, or the two objects, times the velocity cosine of the angle, because that's the x component of the velocity that we're looking at. So that's what's in the x direction. What's in the y direction, I'm going to do the same thing, except now I've got this car that's coming in from this spot, and we end up having it go together. And then we've got m1 plus m2 velocity sine of the angle. So I've got two parts of I have two equations now, which is really good because I have two unknowns, right? The unknowns that I have are the velocity, magnitude of the velocity, and the angle itself. So if I've got two equations, so let's write out the two equations. So I have m1 v1 is equal to m1 plus m2 v cosine of the angle, and I have m2 v2 is equal to m1 plus m2 v sine of the angle. So I could do a couple of different things. I could solve for velocity and do that one first. Or I could solve for the angle first, and actually that one's the easier to do because of the way this particular equation is set up, right? If I want to do that, I'm going to have remember that sine of the angle over cosine of the angle is equal to the tangent. So I'm going to use the mathematical trick of dividing these two equations. So I'm going to get m2 v2 divided by m1 v1 is equal to m1 plus m2 divided by m1 plus m2 v sine of the angle cosine of the angle. Those cancel, and my tangent is just going to be the ratios that I have. So if I go back and I look at what the problem was, the problem said that M2 was 10 kilograms, and it was traveling at 4 meters per second, and the other one was 5 kilograms, and it was traveling at 2 meters per second. That's going to give me my tangent of my angle. And that's 40 divided by 10, so it's 0.4. No, 40 divided by 10 is 4. See, I'm not doing so good today. Gives me an angle of 75.96 degrees, or about 76 degrees. Once we've got that, we can plug back into either of the two equations. So we'll do that. We'll do our 40 kilogram meters per second. This is m2v2 is equal to the sum of the two, which is 10 plus 5. V is the thing we don't know, and it's the sine of 76 degrees. So I'm going to get my 40 kilograms meters per second divided by my 15 kilograms is equal to V sine 76 degrees. That makes sure that my units are right. I'm in meters per second. So I'm going to take my 40 divided by 15. That's going to give me 2.67 divided by the sine of 76 degrees is equal to the velocity. Zoom tight. I feel your pain. 2.75 meters per second. And by the way, we all know, because we've seen it, right? That collisions If I have a mass moving at a small mass moving at a big speed, or a big mass even moving at a small speed, if it's colliding with something, that's usually, the one with the greater momentum is going to win. So I'm going to give you a piece of advice because it happened to me last night, and it turned out it happened to my husband yesterday afternoon. And I'm sure it's because of the weather, but both cases, we were backing out of a parking space. Both of us were on campus, by the way. We were backing out of a parking space, had looked all the way around, did not see anybody. And as we start backing, all of a sudden there's somebody there. Now he did it during the day when it was still light outside, although gray. I did it last night when it was totally black outside because I have a late night class and it was raining. And so if you are walking in the parking lot, please be aware of people backing out. Because if you are wearing dark clothes and dark jackets, you're blending into the background and you're not going to be seen. And momentum tells you you are going to lose. Even if you're the pedestrian that has right of way, you are going to lose. So be careful. It also really bothered me that it was the person who actually saw my lights backing off. And it was very rude afterwards. But I'm going, there wasn't even anybody in the parking lot when I got into the car. Because I know, because I looked around. So please be aware. Because you will lose. And as my mother always said, even if you're the pedestrian in the crosswalk and you have the right of way, if the car hits you, that just gives you the right to sue them after you're dead. So please be aware. And now with everybody texting and not looking, please be aware. Because it is not a good plan. So, especially right now, because nobody can see diddly squat. So that gets us to that particular collision that we just looked at was a totally inelastic collision because the two objects went off together. But you can also have collisions that are glancing blows, okay? So that you have a collision that this one is hitting off one direction and causes that one to go off in that direction. Conservation of momentum is still there. So when you're doing these kinds of collisions, going ahead and keeping track of your X and Y and the befores and afters are really, really going to help. They're really going to help you out a lot. So I'm going to go back and do another one that's kind of like that, except we're going to do this one. All right, this one we're going to have a mass that's 0.2 kilograms. The velocity is equal to 2 meters per second. We've got another one that is 0.3 kilograms, and the velocity when we start is equal to 0. But after the collision, this would be kind of a glancing blow. We've got one that's going off at 1 meter per second, and we're told that that's at 53 degrees. And we have the other one coming off, and this is the 0.2 kilogram object. This is the 0.3 kilogram object. But we don't know this velocity. That's the velocity we don't know. So we're going to set it up the same way. We've got our X and our Y. So the momentum before we have nothing in the Y direction. Neither one of these were traveling in the Y direction. This was just sitting there. This one wasn't. Neither one of them is traveling in the Y direction. We know that one, that's M1, B1, and I'm going to go ahead and calculate it out just because it's going to make life a little easier. It's 0.2 kilograms times 2 meters per second, and I'm going to end up with 0.4 kilograms meters per second. Now this time, the after part, I'm going to have M1V, and that's the cosine of 53 degrees, plus this one has the M2V final cosine of the angle that I don't know. In the y direction, I'm going to have M1V sine 53 degrees plus M2V final sine of the angle that I don't know. So I'm going to go ahead and put in some numbers here. I'm going to do my mass times my cosine of the 53 degrees for this one. So my mass is 0.2 cosine of 53 degrees, and I get, this is 0.12V plus, I get my 0.3V final cosine of the angle. This V we're told is 1 meter per second, so this becomes 0.12 kilograms meters per second plus 0.3V final cosine of the angle. So if I come down here and I write it, I get 0.4 kilograms meters per second is equal to 0.12 kilograms meters per second plus, we've got our 0.3 velocity final cosine of the angle. That's from the x direction. Yes?
How come on the actual diagram you have 1.0 meters per second instead of the 2?
Because this is the after.
Okay.
We've measured it, or we found out some way to determine it after.
Okay. And so, and then down here on your sine 53, is that supposed to...
That's for this
Oh,
one.
okay, no, I see. I misread the number.
You're good.
My bad.
You're good. You're good. Everybody over there, you guys good over there in Tonkawa? You guys with me so far? Okay? Yeah, this, we have to have something that tells us afterwards. If it's going 2 meters per second, we got a problem.
Gotcha.
Something's happened in the collision. If it's going 2 meters per second, this one probably didn't move anywhere. Yeah, I have to give you some additional information in order to have it figured out. All right, and then we do this next one. I've got, we can plug in numbers, and if I plug in numbers, I get my 0.2, I get my 1 sine of the 53 degrees, I get my 0.3 times my V final sine of the angle, and that gives me 0 is equal to 0.2 sine 53 degrees. Gives me 0.16, and that's kilograms meters per second, plus 0.3 V final sine of the angle. So I got 2 equations, 2 unknowns, and now I can solve for the other things. So what I'm going to do is going to clean this up here. I'm going to get 0.4 minus 0.12. Gives me 0.28 equal to 0.3 V final cosine of the angle. I'm going to go ahead and move that over there. Gives me 0.93 is equal to VF cosine of the angle. If I do the other one, I get a negative 0.16 is equal to 0.3 V final sine of the angle. Gives me a negative 0.53 is equal to V final sine of the angle. I'm going to go ahead and do that same trick to get the tangent. So the tangent of the angle is going to equal my minus 0.53 divided by my 0.93. And I'll do that. I can't even punch into the calculator right today. I get a negative 29.8 degrees, which is good because that angle is below the horizontal. So that's a good thing that we ended up with a negative angle. That tells us we're on the right track. And so now I can plug in, I can do my 0.93 divided by the cosine of the negative 29.8. Gives me 1.07 meters per second. So this one is going to travel off at the 29.8 degrees at a velocity of 1.07 meters per second. And if you do explosions, because I think some of the books like to do these, that you've got a something that explodes from the inside, and you have a piece that goes here, and you got a piece that goes here, and you got a piece that goes there. You're going to do the same thing. You're going to do your x and your y, and the initial momentum was 0 and 0, and then you've got whatever your afters are, so that you can play with those aspects. Now, has everybody started the homework, I hope? Because it gives you a chance to ask questions, right? So we're going to work one. We're going to work the basketball problem. Everybody has seen, hopefully everybody has seen the basketball trick. And the basketball trick is this. You take a basketball and you have a tennis ball on the top. And you're going to drop it. So it's going to go and it's going to hit the ground. After the collision, what happens is the basketball goes up and the tennis ball kind of gets shot up into the air. And the question is, how high does the tennis ball get? Okay, that's the fundamental question, is how high does the tennis ball get? Well, we have to use what we know before, okay? So we're going to start, the tennis ball is going to have a mass. In my notes I have it having a mass of 57 grams. The basketball is going to have a mass of 628 grams. And we're going to drop it from a height of 1.1 meters. I'm going to warn you right now that the algebra gets ugly. Okay? Algebra will get ugly in this one. I will warn you that keeping straight the subscripts does help. Okay, that does help. And everybody has seen, if you haven't already heard it, it's that when you see in a book and you're reading your upper division books, it'll say it can be easily shown that, or it'll say, you know, with a little bit of algebra, or it's obvious that. Okay, easily shown with a little bit of algebra, and it's obvious that. Well, when it says with a little bit of algebra, go ahead and expect 3 pages of algebra. If it can easily be shown that, expect 5 to 10 pages. And if it's obvious, it's an act of God. Okay? You know, it's just one of those, you know, you sit there and you're going to be working on it forever. But if it's a little bit of algebra, expect 2 to 3 days. So we're going to do the little bit of algebra one. Alright, so one of the things we got to do is think through this problem. If we're dropping the basketball, first thing we're going to do is we're going to assume no deformation of the basketball and the tennis ball, which is not quite true, but we're going to assume it. We know that if the basketball falls 1.1 meters, the tennis ball is going to fall 1.1 meters. It's just not going to hit all the way to the ground. Okay? That's just not going to hit all the way to the ground. We also know that when the tennis ball hits, or the basketball hits, the tennis ball is still going down, and the basketball is going to instantaneously start going back up, and we're going to get a collision with the tennis ball. So when we start playing with the directions of velocity, you have to think of what is happening at the exact instant of the collision. This is going to come in, it's going to rebound, but the tennis ball is, when it rebounds, the tennis ball is still falling down. So we're going to have that, the directions are going to come into play. So that's what's going to happen to us. But the one thing that we do know is we've got conservation of energy. So mgh is going to equal to m 1/2 mv squared, because whatever potential energy I put into the system, at the instant the collision occurs, I'm going to get the rebound. So I can figure out the velocity of the basketball and the tennis ball just as it hits, right? Mass doesn't matter, I don't have to worry about it. I end up with the square root of 2gh, which we've probably seen ad nauseum by now. And we end up with my velocity. So if I do that, if I put in my 2 times 9.8 times my height, which was 1.1, I'm going to end up with a velocity of 4.7 meters per second. So I've got my initial starting Phys. Okay, so initially, we're going to use the velocity of the ball, and this is the basketball, and we've got the velocity of the tennis ball. Okay? But at the instant of the collision, the velocity of the basketball is going to switch, become up, and the velocity of the tennis ball is going to be going down. We're going to assume this is an elastic collision. And if we assume this is an elastic collision, it gives us another equation that we can play with. Okay? Elastic collision has a special condition, and the special condition is the conservation of kinetic energy. So we're going to start out with the mass of the basketball, the velocity of the basketball before, plus the mass of the tennis ball, the velocity of the tennis ball before, is going to equal the mass of the basketball, the velocity of the basketball after, plus the mass of the tennis ball, the velocity of the tennis ball after. Okay? Now, I'm going to use my kinetic energy conservation to help me out. And this works because we have an elastic collision. So, I'm going to get 1/2 the mass of the basketball, velocity of the basketball squared, plus 1/2 the mass of the tennis ball, the velocity of the tennis ball squared, is equal to 1/2 the mass of the basketball, the velocity of the basketball after squared, plus 1/2 the mass of the tennis ball, the velocity of the tennis ball after squared. Good news is we can get rid of all those halves. Got it? Is that what you needed? Okay? We can get rid of all the halves. We can multiply everything by 2, make life a little easier. I'm going to be over here. I'm going to get the mass of the basketball, velocity of the basketball squared, plus the mass of the tennis ball, velocity of the tennis ball squared, is equal to the mass of the basketball, velocity of the basketball after squared, plus the mass of the tennis ball, velocity of the tennis ball after squared. I'm going to put the basketballs on one side and the tennis balls on the other side. Okay? All I'm going to do is put the basketballs on one side, put the tennis balls on the other side. The mass of the basketball minus the mass of the basketball after squared basketball or tennis ball okay, I want you to be sure that we got this straight. This was on this side, so it's going to stay over here. This had to subtract from that side, so that's why it's over here with a negative. This one had to go over here to give us a negative. Alright, so everybody remember college algebra, right? And we all hated college algebra. Because this is what we spent the whole time in college algebra doing. Which I think is crazy, because this is about the only time we do it. Remember in college algebra, you learned all of those methods for factoring. You learned all those lovely methods for factoring. This is one place you get to use it. Okay? This is one place you get to use it. So we're going to factor these lovelies. So I'm going to get the mass of the basketball, and I'm going to end up with the mass of the ball minus the mass after times the velocity of the ball plus the velocity of the ball after is equal to the mass of the tennis ball, the velocity of the tennis ball after minus velocity of the tennis ball, velocity of the tennis ball after plus the velocity of the tennis ball. So we've actually gone in and done the factoring. Now I will tell you that when I was going, way back when, before we had such a thing as the internet, before we had such a thing as graphing calculators, before we had such a thing as, my first calculator, by the way, cost me over $500. And it was really impressive. It could actually do cosine functions. It was really cool. So, I mean, you have to think about where we were. Slide rules, I was the last class that had to learn how to use a slide rule. So slide rules were important. So factoring was very important because it allowed you to solve problems. Now that you have graphing calculators, it's been a lot easier. We all can go straight to the quadratic equation. It makes life so much easier. And so those skills of factoring aren't as critical as they were when we were going back there. But we still use them to do things like this. So we're going to go back and we're going to look at this one right here. Okay? This one right here, because remember we said at the instant I have a negative. So I'm going to rearrange this problem with the change in signs associated with that initial collision. If I do that, the mass, I'm going to start here so we can see the mass of the basketball, the velocity of the basketball, plus the mass of the tennis ball, the velocity of the tennis ball, is equal to the mass of the basketball, velocity of the basketball after, plus the mass of the tennis ball, the velocity of the tennis ball after. Now, at the instant the collision occurs, the velocity of the tennis ball is equal to the minus the velocity of the basketball. That was that whole discussion about why we do that part. So if I do that, what this ends up being is the mass of the basketball, velocity of the basketball, minus the mass of the tennis ball, velocity of the basketball, is equal to the mass of the basketball, velocity of the basketball after, plus the mass of the tennis ball, velocity of the tennis ball after. Put that in, I can factor out VB, and I get the mass of the basketball minus the mass of the tennis ball is equal to the velocity of the basketball, which is equal to mass of the basketball, velocity of the basketball after, plus the mass of the tennis ball, velocity of the tennis ball after. Okay. Hang on. What are you saying?
Mass of the ball, the last part, mass of the tennis ball, velocity, the tennis ball. Is that A?
That's an A. These are afters. This is on the after side.
Okay. Thank you.
Yeah, that's on the after side. Oh, no, I'm gonna finish that one. Okay, so we've got this one from our tennis ball example. We've got this one from conservation of energy, or conservation of kinetic energy. You can play mathematics with using this kind of an equation here, that you can get that if I take this one, let's do this one. I'm going to not change my sign because we'll come back and do it. I'm going to not change my sign, and I'm going to put my basketballs on one side and my tennis balls on the other side. Okay, I'm going to take my basketballs on one side and my tennis balls on the other side. And I'm going to get my mass of my basketball velocity before the basketball minus the mass of the basketball velocity of the basketball after is equal to the mass of the tennis ball after, velocity minus the mass of the tennis ball velocity of the tennis ball before. Factor out my masses. I get mass of the basketball minus velocity of the basketball after is equal to mass of tennis ball, velocity of tennis ball after, velocity of tennis ball. Okay. So doing this, I can plug this back into that one and get rid of some stuff. And essentially what we're showing you here is that if I plug this back into here and play with it, get it really nice and fun, you end up with the velocity of the basketball plus the velocity of the basketball after is equal to the velocity of the tennis ball plus the velocity of the tennis ball after. This going back into there, cleaning it up, playing around with it, you can ultimately get rid of a whole bunch of terms, and you can show that that happens. Which means, if we know that the velocity of the tennis ball is negative the velocity of the basketball, okay, we know that we show that, we end up with the velocity of the basketball after is equal to 2 times the velocity of the tennis ball plus the velocity of the tennis ball after. So, because we've used our equation, we get mass of the basketball minus the mass of the tennis ball is equal to the velocity of the basketball, which is equal to the mass of the basketball, velocity of the basketball after, plus the mass of the tennis ball, velocity of the tennis ball after. I'm going to plug that into there, and you get the mass of the basketball minus the mass of the tennis ball. Velocity of the basketball is equal to the mass of the basketball minus 2 velocity of the tennis ball plus velocity of the tennis ball after plus mass of the tennis ball, velocity of the tennis ball after. We're going to, and we know that that is the velocity of the basketball. So now we rearrange and clean things up. We get mass of basketball minus mass of tennis ball. Mass of basketball is equal to minus 2 mass of the basketball, velocity of the basketball, plus mass of the basketball, velocity of the tennis ball after, plus the mass of the tennis ball, velocity of the tennis ball after. I'm going to put this on this side. So I end up with mass of the basketball minus the mass of the tennis ball plus 2 times the mass of the basketball times the velocity of the basketball is equal to the mass of the basketball plus the mass of the tennis ball, velocity of the tennis ball after. This ends up giving us 3 mass of the basketballs minus the mass of the tennis ball divided by the mass of the basketball plus the mass of the tennis ball. Well, velocity of the initial velocity of the basketball equals the velocity of the tennis ball after. So we can plug in numbers because we have all those numbers. So you get 3 times 628 minus 57 divided by 628 plus 57 times 4.7, because we figured that out earlier, gives us 12.5 meters per second is the velocity of the tennis ball after. But we wanted to know how high the tennis ball went. That's easy. 1/2 mv squared is going to equal mgh. Once I know the velocity, h is equal to v squared divided by 2g, which gives us, it's going to end up being 8 meters. Or you can use your kinematics equations if you want. Because my kinematics equation says v squared is equal to v initial squared plus 2ah. In this case, my initial velocity right at the collision at that point goes away, and I end up, or I go the other way. I end up going the other way. I go ahead and get rid of the final velocity at the maximum height, and I end up getting v squared divided by 2g is equal to h, which is exactly what we get from the conservation of energy. So just whichever way you want to do it, whichever way you're more comfortable doing it. So like that one is just a pain in the algebra. The trick to it is the fact that you have to use both ideas, conservation of energy and conservation of kinetic energy in your elastic collisions. Oh, so let's do another one. I like doing pinball, because pinball's fun. So in pinball, what we do is we have a spring. And our spring, we're going to give it a spring constant of 20 Newton meters. It's going to hit a ball. Okay? Our ball, we're going to say it's 0.25 kilograms. we're gonna end up hitting it. Okay, use conservation of energy to hit it. I'm gonna do it this way. We're gonna go up, okay? We're gonna use conservation to hit it. We wanna find out how high we're gonna go. So that's one thing that we can figure out. So that's just our conservation of energy problem. So I'm gonna get potential energy of the spring is 1/2 kx squared, which is gonna equal 1/2 mv squared. We can find the initial velocity that we're gonna end up going if we compress this 1 centimeter. So if I do that, halves cancel, I get k over mx squared is equal to v squared. I've got 20 Newton meters divided by 0.1 meters. And that's divided by 0.25 kilograms, that's when my units are getting funky. 0.1 meters squared. This gives me 0.8, and I have to take the square root of that to get my velocity. Gives me 0.9 meters per second. Find this, it's just mgh is equal to 1/2 mv squared. Get rid of that again. H is going to be v squared over 2g, which is going to give me 0.9, or actually it's 0.8, because we already figured that out, because we kept it, times 2.98. Gives me 0.04 meters. Which is probably typical in a pinball machine. But we can do that if we think of the situation being the carnival game where I'm hitting an object with a collision. Now we can go and say, okay, we know how we're going to hit it and get our collisions up there. So we can play with these different things using the different things that we've had in order to get the information that we need. You may have problems that look like this. We have a target. We've got the bullet that goes through the target. We know the initial velocity of the bullet. Let's say the initial velocity of the bullet is 80 meters per second. When it comes out, it's going to have a velocity of 40 meters per second. We may want to look at what the velocity of the target is. We may want to look at the loss of energy. We can look at the loss of energy a couple of different ways. So we can look at these problems in a number of different aspects. That gives us our ballistic pendulums, it gives us our two-dimensionals, it gives us a variety of different pieces. Let's see if I got another problem in here. Done that one. We've done our two-dimensionals. I think, guys, guys, we've done just about everything. So I will put this up. I think I have in the homework, there's one other concept but we've already talked about it, and you won't be tested over it at all, because I don't like doing it on the test. But instantaneous thrust is equal to mass times acceleration, mass times my change of velocity at temperatures. And so if I'm doing instantaneous thrust, I can use speed and the change in mass over the change in time. And that's my rocket propulsion. I think I only have given you guys like one question for it on that one. But basically what we've done is we have linear momentum is equal to mass times velocity. We've got that Newton's second law could be written as the change in momentum is equal to the impulse. So we have impulse type problems. The key is looking at the momentum before equaling the momentum after. And then if I'm doing the two-dimensional ones, setting up your grids to look at your two-dimensional ones. The key for elastic collisions, and you're probably going to see this question over and over again, that elastic collisions have the special case that kinetic energy is conserved. Kinetic energy is conserved. And in inelastic collision, only momentum is conserved. But energy, total energy is always conserved. It's just whether or not that we can assess it on both ends. So I think that gets us through this chapter. I will post the videos, because I usually show a whole bunch of videos, and I'll let you guys look at those on, on your own time, because I'm not fighting with technology right now. I had trouble broadcasting from my rooms last week, and it's like, I'm not going there today. I'm just not going there today. It's not a good plan. But I'll post those momentum ones with the hockey and everything so that you got it. And we'll see you all on Wednesday. You guys good over there in Tonkwall?